Hello class, this is Mr. Lane, and today we want to talk about the combined gas law. Alright, so up to this point we've talked about Boyle's law, Charles' law, Day-Lussac's law, and we said volume is inversely related to pressure, and we said that this formula represents Boyle's law. We said that temperature is directly related to volume, and vice versa, and so the red formula is Charles' law. And then lastly we looked at Day-Lussac's law, where pressure and temperature are also directly related. Alright, so our purplish one is Day-Lussac's. Now you notice here, volume and pressure are always on top. There are numerators. Temperature is always on the bottom of our ratios, denominator. And so we can combine these three formulas into one combo formula called the combined gas law, because in the real world, often we have volume, pressure, and temperature changing. So you plug these three formulas in together, and this is what we get. We get that the starting volume times the starting pressure divided by the starting Kelvin temperature is equal to the final volume times the final pressure divided by the final Kelvin temperature. Alright, so this tips, again, I always like to provide tips. You have to use Kelvin. Pressure you can use any unit. The pressure has to be the same on both sides. Volume, once again, use any unit. It could be liters, milliliters, cubic centimeters. But whatever you use on one side, you have to use on the other side. So you might have to do some conversions to get the same unit for volume on both sides, or pressure, or temperature. Alright, so let's look at a problem here. Let's say we have, I'll try to draw a balloon here. So we have a balloon. Let's say this balloon is 11 liters in size. The balloon starts out, we're at sea level. So we got 1 atm of pressure. And let's say the temperature, is 20 degrees Celsius. Alright, so this is what everything is starting out as. What is it going to end up as? So in the end, let's say that the day is a nice day, so temperature goes up. Let's say temperature goes up to 30 Celsius. We're trying to figure out how big the balloon is going to be. And let's say some stormy weather rolls in, and that causes the pressure to drop just a little bit. So it didn't storm yet. It's a nice day, but you see some rain clouds moving in, so pressure dropped by just a little bit. Because as pressure goes down, it tends to correlate with atmospheric conditions, lifting of air, which creates rain, creates storms. Alright, so we're going to plug these numbers into our formula. So V1 is 11 liters. We're going to times that by P1. And we're going to divide that by T1. T1 is 20 plus 273. So it's 293 Kelvin. Alright, so these are our initial conditions. Final conditions, we're solving for V2. Pressure is also in atms, so we're good here. We don't have to convert. This is an easier problem. And 30 plus 273 is 303 Kelvin. Alright, so pressure is dropping. That results in the balloon getting a little bit bigger. Temperature is also increasing by a little bit. That will result in our balloon getting a little bit bigger. So our answer needs to be greater than 11 liters. If it's not greater than 11 liters, then we know we did something wrong. So let's go ahead. We cross multiply. So we're going to take, oh, my mouse is going crazy. We're going to take, I am not pressing anything here. My finger's doing that. 11 times 1 times 303. So 11 times 1 times 303. So go ahead and pause this, see what you get for an answer. It's 3,333. And that's equal to 293 times 0.97. Which is 284.21 times V2. And we need to divide both sides by what we're multiplying V2 by, which is 284.21. So 3,333 divided by 284.21. We get about 11.7. So V2 is equal to 11.7 liters, which is bigger as we expected. So that's how we use the combined gas law. Let's do one that's a little bit more challenging. Let's do another picture here. So let's say we have in the balloon, let's say our balloon is 20 liters in size. The pressure, once again, let's start out at sea level. And let's say the temperature, nice sunny day, 30 Celsius. We're going to climb to the top of Mount Everest with our balloon. And up here on top of Mount Everest, the conditions are very little air up here. Air becomes very, very thin because you're above like 2/3 of the Earth's atmosphere. So you only have about 1/3 of the Earth's atmosphere weighing down on you. So the air is about 3 times less dense. It's about 0.34 atmospheres of pressure up here. And the temperature is about -20 degrees Celsius ballpark. So how big will your balloon be now? Alright, once again, pressures are in the same system, so we don't have to do that conversion. So we're going to take V1, 20 liters, times it by the initial pressure, 1 atm, and divide it by the initial temperature, 30 plus 273 is 303. Final conditions, we're going to take V2 times 0.34 atm, and divide it by -20 plus 273, which is 253 Kelvin. So temperature is decreasing by about 15–18%. So that's going to make the balloon get smaller, but pressure is decreasing by about 2/3, and so that should make the balloon get about 3 times bigger, right? So if pressure is being decreased by a factor of 3, the balloon should triple in size. So we have conflicting information, but the pressure change is bigger than the temperature change, so our balloon should get bigger. So let's see what happens. So once again, cross multiply 20 times 1 times 253. This is 20 times 253, which is equal to 5,060. And that is equal to 303 times 0.34, which is 103.02 times the final volume. Get V2 by itself, divide both sides by 103.02. So 5,060 divided by our answer from previous question. We're looking at V2 is equal to 49.1 liters. So pressure won out. The pressure change was a greater magnitude than the temperature change, so the balloon got bigger, much bigger, about 2.5 times bigger. So that's the combined gas law, so hopefully this helps. Have a great day.